important spot in our understanding where we were getting to this idea of an ellipse. Now, here's the thing about an ellipse that is really, really cool. Is that you have your two focal points, okay? And when you draw an ellipse, the focal point is, when it's here, it's closer to this edge along the major axis than anywhere else, okay? But here's the thing about an ellipse that's important. If I start at one ellipse, or one focal point, and I walk to anywhere on here, so I'm going to take a walk from focal point 1 to anywhere on the ellipse, and then I'm going to walk to the focal point 2. Is that cool? Now, we can call these D1 and D2. I'm going to do the same thing, but I'm going to choose a different point on the ellipse. Let's say I'm going to choose right here. We'll do a little symmetry here. Oh my gosh, what was that? Okay? If I look at green's D1, or we'll call it D3, and this is D4, what do I notice about the first walk for green compared to the first walk for purple? So it's longer, true? But what do I notice about the second part of my walk for green compared to purple?
Shorter.
It's shorter. That's interesting, right? If we do it again, let's do a blue. I'm going to walk to right here. I'm going to walk all the way this way. What do I notice about blue's first walk? It's very small. True? But what about blue's second walk? It's very long, yes? So we'll call this D5, and we'll call this D6. If you had to make a guess, if there was a relationship there, what do you think that relationship might be? Check your neighbor now. See if your neighbor knows.
So the one in Kepler's law, where the areas are this thing.
Oh, that's a different one. We're going to do that one.
Oh, that's where this was going.
Yeah, this is just about the distances.
Just the other Kepler law, that's like T squared equals
No, we're going to talk about that today too. This is just a property of an ellipse. All right, who knows? So if I added up D1 and D2, what do you think might be true about it? So this is the property of an ellipse, is that no matter what point you draw on the ellipse, okay, no matter what point you draw on the ellipse, if you walk from one focal point to that point, to the other focal point, the total trip is the same. Yeah?
What's the difference between D5 and D6?
So D5 is to this point here, and D6 is from the point on the ellipse to the other focal point. So D1, D2.
Well, you drew an extra point, like on the actual border. Okay.
That's here, yeah.
So you can like bounce anywhere across, that's what you're doing.
Yes. Yeah.
Is it like straight distance or displacement? Like would that D5 distance be negative?
No, it's distance. It's just distance. It's how far you walked. And you know what's really cool about this? Is it's also that's equal to the major axis. Because if you started here and then walked to this edge and then started at this point, walked to this edge, and then walked to the other focal point, it's like the same thing as walking from edge to edge. So that is a property of an ellipse. Now, that in itself doesn't really doesn't really do much for us. Like, that's just what an ellipse is. Okay? So you can see anything looks like an oval, but it has to have this property for it to be an ellipse. Is that cool? All right. Let me draw another ellipse, or try to at least. They're very hard to draw. Oh, God. So, again, we're going to have two focal points. And the focal points are closer to the edges than anything else. That looks all right. That's good enough. Looks like a cartoon face, doesn't it? So let me draw in the major axis. And the minor axis. Is that cool? All right. So here's the ellipse, and what it turns out is that before the 1400s, people who thought about these things thought that and we're talking about European science, Western science, not anything else. There are other peoples in the world who thought other things. I just am not knowledgeable about it. They thought that everything revolved around the Earth. Because that's our actual experience, is that things revolve around the Earth. Like, what do you notice about the sun each day?
It moves.
Sun goes across the sky, right? The sun goes across the sky, and then, 12 hours later, it starts back here. So you could easily infer from that that the Earth goes around, or that the sun goes around the Earth. Right? Absolutely. Just the same way we infer that, the moon must do the same thing. The moon must go around the Earth because, we see it differently and we see it go and come back, right? These are all very reasonable inferences. The problem is that if that idea were true, then the other things we saw in the night sky would follow a similar pattern. And it turns out that the planets, if you watch them over multiple nights or over multiple months, depending on how far away they are, they don't do that. They do other things. And so there was a guy named Nicholas Copernicus, and he was a Polish monk, and he was looking up at the sky, and he's like, I don't think that's right. He's like, this just doesn't make any sense. And people have all these really elaborate reasonings, right? These elaborate drawings say like, well, this is why, right? Everything's still going around the Earth. But if you add these 14 complications, it can explain the motion of the planets. And he's like, that doesn't make any sense at all. So what scientists are always doing is they're trying to look for the simplest explanation for stuff. And Copernicus was like, the simplest explanation is that the sun is at the center and everything's going around the sun. He's like, if you just do that, then literally everything makes sense with zero complications. But that's not what the church was teaching, and he was a monk, so he's like, I can't tell anybody this. He's like, people would freak out. And so he wrote the papers and he put them underneath his bed, and then literally, like on his deathbed, right before he died, he was like, listen, there's some really important stuff, it's in the papers, it's underneath my bed, and then he died. And people had to sort through it and figure out what he was talking about. Because if you go against the church teachings, people get really upset. They even want to get excommunicated. That sounds bad. I don't even know what that is, but it sounds bad. So he was the first one to come up with this idea. But because it made so much sense, it pervaded the scientific community in Europe very, very, very quickly. And what he said was that everything is revolving around the sun. Right? Everything is revolving around the sun. And what this literally led to was a change in our complete paradigm of the way that we saw the world, our place in it, and science as a concept. And it led to something called the scientific revolution. Right? Well, but think about this. The word scientific revolution, we have taken that word revolution to mean a change in the way that we understand things. But literally it comes from the word revolve, which he said everything revolves around the sun. So the scientific revolution just came from Copernicus coming up with this idea that everything was revolving around the sun, and it gave rise to a whole new word, which now has a whole new context. How cool is that? I think that's like the coolest thing. So the scientific revolution comes out of this, and then we get Galileo, who's like, yeah, that totally makes sense, right? And what happened to him? The church made him kill himself, right? So Galileo was like, yeah, this totally makes sense. And they're like, no, it does not. Yeah?
So Galileo wasn't the first person, it was the Polish monk that you were talking about?
Yes, Nicholas Copernicus is his name. He was the first one, okay? And then Galileo was like, oh, absolutely, that makes sense. Because even with a small telescope, you can look up and you can see 4 moons of Jupiter. And they go around Jupiter. Like, you can watch them, right? Now, in the night sky, they don't look like they're going around. But if you look at Jupiter, okay, you'll see 4 tiny little pinpricks of light. And then they are at different places. They're all in the same line now because they all revolve around in the same plane. And then if you just watch them, you got to move the telescope because the Earth is moving, the Earth is rotating. But you'll see it here, and then sometime later, this one will be here, and this one will be here, and like this one will be here, and this one will be here. Because what they're doing is they're coming out and then going back in, and coming out and then going back in. So it looks like they move left and right, but what they're really doing is coming out and then going back in, and then coming out and going back in. You can actually see it happen over the course of, let's say, a night, which is so fascinating. So he's like, yeah, those moons, those have to be moons just like our moon. They go around Jupiter just like the moon goes around us. And basically everything's revolving around the sun. There you go. Yeah.
Do they revolve at the same speed?
No. So we know that they're going in circles, so their centripetal force is the gravitational force. So for any moon, mv squared over r is equal to g over r squared. So their speed is dependent upon their radius. So the ones that are farther away have a smaller speed. Does that make sense? You see how this statement is like super useful here? This statement helps us understand all of this stuff, which I think is really cool. So yeah, so the ones that are farther away take longer to go around. That's why even if you look at our solar system, everything revolving around the sun, Mercury, the closest planet, you guys know Mercury is the closest planet. That thing's whipping around, right? Earth takes 1 year, right? Mars, more than 1 year. Jupiter, more than that. Saturn, more than that. And then you go down. So we got Mercury, Venus, Earth, and Mars. Those are the 4 inner planets. We call those the terrestrial planets because they're made of like rocks and stuff. So we call them terrestrial planets. And Mars is 1.5 times as far away as the Earth is. So it's from the sun. So it's like, here's the Earth, it's another half out, and it goes around. And these aren't perfectly circular, but they're pretty close. And then we get to Jupiter. Jupiter is a good 5 times as far away from the sun as the Earth is. But between Jupiter and Mars, there's an asteroid belt. I mean, the whole thing, it's like 1 billion asteroids all going around in the same direction at very close to the same speeds. The outer ones are going a little slower than the inner ones. But it's like 1 billion asteroids. It's a lot. They're very small, yeah?
Is it like one belt, or is it more of like a shell?
No, it is a belt. So you know how Saturn has rings?
Yeah.
This is a ring of asteroids around the sun instead of a ring of icy rocks around the planet. So it's flat and circular. And then, so then we got Jupiter, Saturn, Uranus, and Neptune. Okay? And then outside of that, there's another belt. It's called the Kuiper Belt, of course named after Mr. Belt. And this is another one, and it's outside of Neptune's orbit. And there are some minor planets in that bad boy. So like Pluto's a dwarf planet, Pluto and Eris,
Yeah.
and there are 5.
There's 5?
There's that one named after
I literally
Double
just
line.
looked Pluto, so.
Pluto, Eris, Haumea, and Make. There's 5. So these 4 are in the Kuiper Belt. Okay. These 2 were found with a large telescope on top of a Hawaiian mountain. That's why they got Hawaiian deity names. This one is actually in the asteroid belt. It's the largest asteroid in the asteroid belt. It's called Ceres, C-E-R-E-S. There's a great show on, it was on Sci-Fi, and then it was on, I don't know, Netflix or Hulu. I don't know if these things are, in my head, they're the same. Because you just turn it on. Like, I don't know what I'm turning on. It was called The Expanse, and it's a space science fiction show. And in it, they had colonized Mars, and there's people that lived on Ceres in the asteroid belt, and they were mining in the rest of the asteroid belt. Really interesting show. Anyway, so in the Kuiper Belt, and it's a belt. It's flat, and it's outside of Neptune's orbit, which is a cool thing. Yeah.
And are all the planets on the same plane?
Oh my God, what a great question. The answer is yes. All the planets are on the same plane, going in the same direction, which is fascinating. Okay? I'm going to tell you why. Actually, I'm going to show you a little video and tell you why, because the graphics are better. And yes, and all solar systems are like that. Okay? As are all planets, for that matter, where everything, like all the moons, all of, let's say Jupiter, for example, are all on the same line. Just like all the planets in our solar system are also all along on the same plane, going in the same direction. As are the 2 belts. Now, there's another thing, but it's like real far away. So we call the distance from the sun to the earth 1 AU. That's an astronomical unit, 1 AU. And so we say Mars is 1.5 AU is its average distance, and Jupiter is 5 AU, and Saturn is 10, and like Neptune is like 40 AU. Like these things are far away. But out at 50,000 AU, 50,000 AU, there's a spherical shell of icy objects called the Oort cloud, O-O-R-T, Oort cloud. We know it's there because oftentimes we'll have called long period comets that'll come in. We're like, what the heck did that thing come from? But knowing its speed, we know where it came from. Because if I can measure its speed, I know what its radius is. I know how far away it came from. How interesting is that? Yes?
How far, isn't there like the Voyager probe, or like what's the farthest like man-made object that's been out?
How far is the Voyager? That's a great question.
Isn't it the one where we took the pictures of
Let's
Brazil
check.
and something?
Those things were launched a long time ago.
Like 2001.
I mean, a long time. Okay. All right, here we go. Launch date. This one's 77. It's funny, Voyager 2 was launched first, but it was started to build second. 43 years. That's cool. What's that?
That's a long time.
I know. It's been in space for 43 years. It's 14, I don't know, what is it, a gazillion miles? But the thing that's important is it's 152 AU away. 152 Earth radii away. That's what an AU is.
What's 1 AU?
93 million miles. That's the distance from the sun to the Earth. Average. It's going at 38,000 miles per hour. And I love this one. The one-way light time is 21 hours. How cool is that? Like, it takes a light from there, or a radio signal, or whatever, 21 hours to get to Earth. It's that far away.
Because light's like so fast.
So fast.
Wow.
Isn't that cool?
So like if they try to communicate with that, there's like a 21 hour delay.
Yeah, have you ever seen, What's the Matt Damon one? Man, I love Matt Damon.
Martian.
The Martian. You guys know that? I love Matt Damon. Like, I want to be like Matt Damon when I grow up. Like, he's so cool. I just love that guy.
That's like when I grow up.
He's like 2 years older than me, but when I grow up, I want to be Matt Damon. The Martian is this great movie because he's got to send a signal to Earth. It takes 20 minutes to get there. They have to formulate an answer and send one back, and it takes 20 minutes for it to get back. So he's got to like wait all this time, and it's like seriously problematic because if you, I'm gonna get rid of this thing. Taking up too much real estate. So if you think about, here's the Earth, okay, and then we'll put the sun. Where's my orange? There's the sun. So this is the distance to the Earth. I need another half. Okay, there's Mars. So at its closest, okay? So the time, this time for a light signal is 8 minutes. So at its closest, this would be about 4 minutes. Does that make sense? But these things are moving, and we know because the Earth's radius is smaller, it's actually moving faster. Does that make sense? So if you look, let's say even if you went 3 months, you're here, okay? Because it's 12 months to go around, so 3 months is a quarter. Does that make sense? What did Mars do? It didn't move nearly that far. Now look at the distance. All of a sudden this distance is far. You see the problem? At its farthest, if the Earth were here and Mars were here, we know this is 8 light minutes, this is another 8 light minutes, and then this is another 4. So at its farthest, it would take 20 minutes for a signal just to get to Mars, and then another 20 minutes to get back. See how that works? Yeah.
Do you know how often the Earth and Mars are 4 light years away?
How often? Okay, so this is called opposition. What is this one called? I don't. It's not super complicated, but this is going around and this is behind it. And so eventually it's going to catch up. Does that make sense? We'd have to look at the animation. I don't actually know. So yeah. In the Matt Damon movie, when you have to communicate that way, you have to wait. And that is like a huge deal. Okay? It's a huge deal. You cannot have two-way conversation if you're off the surface of the Earth. I mean, if you're close in low Earth orbit, but if you're on your way to the moon, it's like...
Because there's such a delay. It's like,
Yeah. Exactly. Even at the moon, it's still only 1 second, but you have to like give your whole message out. It's going to take a second to get there, and you got to wait for your whole message back. It's a whole thing. What's that?
I said, I guess you can't have arguments when you're in space.
No, I mean, not really. Or at least you have time to like formulate a full argument. Okay, and you'll see that idea represented in these movies. That